Hi, I'm Zach Tatlock, and this talk is about proving optimizations correct using parameterized program equivalence. I performed this research with Sudipta Kundu and Soren Lerner at the University of California, San Diego, and we first presented it at PLDI 2009 in Dublin. Compilers are one of a programmer's most fundamental tools, and as such, we expect them to be correct. Unfortunately, it's both difficult and time-consuming to develop stable, reliable compilers. Because compilers are large, complex programs with many interacting components, it can often take up to a decade before a compiler is reliable enough for widespread use. It turns out that the difficulty of compiler development has many adverse effects. It leads to buggy compilers, but it also hinders language development and discourages users from extending their compilers with domain-specific analyses and optimizations. The work I'm presenting here focuses on the correctness of one of the most error-prone components of a compiler, its optimizations. Mature compilers have many intricate optimizations, which can interact in unexpected ways. It's very difficult to account mentally for all these interactions, or to even create test cases for all of them. Furthermore, increasingly many systems rely on compiler optimizations for good performance. For example, in JIT-based systems like Java, C#, and now even JavaScript, optimizations are critical for good performance. As a result, disabling optimizations to increase reliability is often no longer an option. There are two dominant approaches to providing correctness guarantees for compiler optimizations: translation validation and a priori correctness proofs. In translation validation, a tool checks that, for each run of the compiler, the transformed output program behaves exactly the same way as the original input program. Note that with this technique, we have to perform the check each time the compiler executes. Some examples of this approach include the initial work on translation validation by Panuli, work by Nekula on translation validation for GCC, Zook et al.'s work on validating loop optimizations, and Tristan et al.'s work on verified translation validators, where the validator itself is proved correct once and for all. The second approach is to directly prove the correctness of the compiler a priori, before it's ever run. This approach is taken by Leroy in the Concert compiler, which is proved correct once and for all in Coq, and by the Rhodium system, where optimizations are written in a specialized language and proven correct once and for all. The technique I'm presenting is fully automated, so here we'll just focus on the fully automated techniques. This leaves Rhodium and all the translation validation work, from which I'll use the work of Nekula and Zook as representative examples. We'll evaluate these techniques along two dimensions. First, we look at the scope of the correctness guarantee. Here, translation validation provides a smaller scope of guarantee because it's possible for the compiler to hit a bug, while the goal of a priori techniques is to eliminate correctness bugs before the compiler ever runs, thus ensuring that every run is bug-free. The other dimension is expressiveness, which considers the range of optimizations a technique can handle. Here, translation validation is the clear winner. State-of-the-art translation validators can check complex loop optimizations, while Rhodium only handles one-to-one rewrite rules, which transform a single statement at a time. The work I'm presenting bridges this gap. It allows even complex loop optimizations to be proven correct once and for all in a fully automated way. Our key insight is that we can generalize traditional translation validation techniques to the setting of once and for all correctness proofs. To better explain how we do this, let's first take a closer look at how translation validation works. In translation validation, for each run of the compiler, we take the input program that the compiler starts with and the corresponding output program it produces and pass them to a tool that determines whether or not they are semantically equivalent. The downside here is that we only know that these two specific programs are equivalent. That is, that this one single run of the optimization was correct. So in our approach, we switch the focus from concrete, fully specified programs to parameterized programs. To give you a feel for what a parameterized program looks like, let's take this concrete program and replace some of its parts with parameters. First, let's take all the instances of the variable k and replace them with the parameter I, which ranges over variables. Similarly, let's take the loop bound of 100 and replace it with the parameter e, which ranges over expressions. Finally, let's take the array update in the loop body and replace it with parameter s, which ranges over statements that can represent arbitrary code, including branches and even loops. We now have an example of a parameterized program in our system, where I can range over variables, e over expressions, and s over statements. Now, while a pair of concrete programs represents a single instance of an optimization, a pair of parameterized programs can be used to express a full optimization, where the input parameterized program represents a pattern for concrete code to match, and the output parameterized program specifies what to replace the match code with, sort of a syntactic find and replace. Thus, while traditional translation validation determines the correctness of one instance of an optimization using an equivalence checker, we determine the correctness of an entire optimization by passing it to a parameterized equivalence checker, or PEC for short. Our PEC tool works by generalizing traditional translation validation techniques to the setting of parameterized programs. Our main contribution is the PEC algorithm for checking the correctness of optimizations. PEC is fully automated, and it checks optimizations a priori, before they're ever run. Our primary advance over previous fully automated systems, like Rhodium, is the ability to prove the correctness of many-to-many rewrites, rather than just one-to-one rewrites. To highlight the power of PEC, we designed a language that uses pairs of parameterized programs to express optimizations as many-to-many rewrite rules. We then wrote and checked the correctness of a variety of complex loop optimizations, which could not have been proven correct or even expressed in Rhodium. For the rest of the talk, I'll first show how to express a simple optimization in our system. Then I'll demonstrate how we check optimizations for correctness, and finally, I'll evaluate the expressive power of our approach by presenting the optimizations we implemented and checked for correctness. For the rest of the talk, I'll use loop peeling as a running example. In general, loop peeling simply moves one iteration outside of a loop and adjusts the loop bound accordingly. Here's a simplified form of loop peeling in our system. This rewrite comprises a left and right parameterized program. The uppercase letters range over elements of concrete syntax. For example, I ranges over variables, E over expressions, and S over statements. The left parameterized program indicates a pattern to match, and the right parameterized program specifies what to replace that match code with. As a result, this rewrite moves the final iteration after the loop and decrements the loop bound by 1. Our rewrite rules also contain side conditions that indicate when the rewrite rule can be safely applied. In this case, E must be positive, and S should not change the values of I or E. Loop peeling is often used to enable other optimizations, like loop merging, or as I'll show here, loop unrolling. Consider this concrete program. Here, we can't unroll the loop body 3 times because the loop bound isn't divisible by 3. However, we can apply our loop peeling rewrite to peel off one iteration of the loop so that the loop bound becomes 99, which is divisible by 3. We perform rewrites in 3 steps. First, we match the parameters to their corresponding parts in the concrete program. In this case, we match I to K, E to 100, and S to the array update. Second, we check the side conditions. In this case, they all hold. 100 is positive, and the array update doesn't modify K or 100. Third, to get the transform program, we now simply instantiate the right parameterized program with the concrete values for I, S, and E. The transform version now has the desired bound of 99 and can be directly unrolled 3 times. Now that we've briefly seen how optimizations are phrased in our system and how they can be applied, let's move on to checking their correctness. PEC comprises 2 main modules. A relate module, which is a generalization of the translation validation techniques developed by Necula for GCC, and a permute module, which is a generalization of Zuck et al.'s techniques for validating loop optimizations. For this presentation, I'll show you a simplified version of PEC's architecture, where PEC will check an optimization by sending it to both the relate and permute modules, and then have each module independently try to show that the optimization is correct. We'll OR their results so that if either module is able to check the optimization, then we'll say that it's correct. Next, I'll show how the relate module can check our loop peeling example, and later in the talk, I'll show a very brief example that relies on the permute module to give you an intuition for how it works as well. We want to show that whenever we transform a program with this rewrite rule, the original and transformed versions of the program are equivalent. To do this, we consider the CFGs of the parameterized programs and say that the 2 CFGs are equivalent if whenever they start in equal states, then they must also end in equal states. Here we use sigma 1 to represent the state of the left program at a point, and sigma 2 to represent the state of the right program at a given point. To show that the original and transformed programs are equivalent, PEC relates their executions. Specifically, it will show that if we run these two programs in parallel, their executions will line up or synchronize at certain points. As indicated by the dotted edges, we'll assume that the programs begin in equal states and require PEC to show us that they end in equal states. Thus, the entry points and the exit points are always related with state equality. PEC will carry out 3 steps to show the equivalence of these programs. I'll briefly describe the steps here, and then we'll go into the details for each step in the following slides. First, PEC finds synchronization points between the two programs. A synchronization point consists of a location in the left program and a location in the right program where the executions of the two programs will line up. I'll show synchronization points as dotted green edges between the locations in the left and right programs. Second, PEC generates initial invariants that hold at these points. These invariants are simply predicates over the left and right states. They're similar to a regular program invariant, except that they talk about the states of two programs and how they relate. For example, the invariant for A could assert that the value of I in the left program is equal to the value of I in the right program. Third, PEC checks that these invariants are preserved. By this I mean that each invariant should imply all of its successor invariants. PEC uses a theorem prover to check all these implications, and in the event that some implication does not hold, PEC will strengthen that invariant and then repeat the checks. Once this is done, we'll know that if the two programs start in equal states, they'll execute in lockstep, and each time they reach a synchronization point, its invariant will hold. Thus, because we have a synchronization point with state equality at the exits of the two programs, they must end in equal states. Using these 3 steps, PEC will be able to relate the executions of the two programs and show that our rewrite rule is correct. Now let's consider each of these steps in more detail. I'll begin by explaining how our tool finds the synchronization points. PEC starts at the entry of both programs and traverses them in lockstep. It'll stop whenever a program is about to execute a statement parameter, like in this case, where the left program is about to execute S. Once PEC has hit statement parameters on both sides, it'll add a synchronization point between those locations in the left and right programs. In this example, we also need to consider the case where the right program doesn't enter the loop, which leads to another synchronization point shown here. Similarly, PEC must consider the case where the left program doesn't enter the loop. However, PEC will be able to prune this case because the left path will never be executed. To see how this pruning works, note from the left path that I will be 0, and that I will also be greater than or equal to E. Thus, from the left path, PEC can conclude that E is less than or equal to 0. Additionally, recall from the side conditions that E is always greater than 0. Because this is a contradiction, PEC knows that this case can never occur, and thus safely ignores these paths. Our tool continues to walk the programs in this fashion, and gathers synchronization points as it goes. As you can see, in some cases, existing synchronization points are rediscovered, except in this final case, where a synchronization point is added between the exits of the two programs. So here we have the final set of synchronization points for this example. Now let's see how PEC generates the initial invariants for these points. As I mentioned earlier, we assume that the programs begin in equal states and require that they end in equal states. Now I'll show you how PEC generates the initial invariants for synchronization points A and B. Again, these invariants are simply predicates over the left and right states, and they initially will include state equality and the strongest postcondition with respect to true up to the nearest branch. Let's look at how this works in our example. Here's the initial invariant PEC generates for A. State equality is required because each program is about to execute a parameterized statement, in this case S. In general, we can only conclude that a parameterized statement will execute the same way in the original and transformed programs if it starts in the same state. The strongest postcondition for this case simply states that I less than E evaluates to true in the left state, and that I less than E minus 1 evaluates to true in the right state. We get this by looking at A and the paths from the nearest branch that lead to A. In particular, the left program has just taken a branch requiring that I be less than E, and the right program has just taken a branch requiring that I be less than E minus 1. Here's the initial invariant PEC generates for B. Again, we require state equality because both programs are about to execute a parameterized statement, and we include the relevant strongest postcondition, which involves these two paths leading to A. Now that we have the initial invariants for our synchronization points, let's move on to how PEC checks that they're preserved. PEC will be able to check that these invariants are preserved by asking a theorem prover to show that each invariant implies all of its successor invariants. Here are the 5 cases PEC needs to consider for this example. In particular, the entry should imply both A and B, A should imply B and itself, and B should imply the exit invariant. As an example, let's look at how PEC handles the A to B case. First, let's look at the path from A to B in the CFGs, which we're seeing highlighted here. And now let's take this exact same path and straighten it out. Alright, here's the query PEC will send to the theorem prover for this case. Let's step through it piece by piece. The query considers arbitrary left and right states and assumes that A holds on them. Furthermore, it assumes that sigma 1 prime is the result of executing the left path starting at sigma 1, and similarly, that sigma 2 prime is the result of executing the right path starting at sigma 2. The step function here encodes how statements execute, and we provide the theorem prover with some simple axioms to define how step works. Now, given these assumptions, the theorem prover must show that B holds on the resulting states. So PEC sends the query to the theorem prover to ask if it's valid. Note how similar this is to a Hoare triple, where some invariant implies another invariant after executing a program. Except here, we're dealing with predicates over 2 program states, and we have 2 programs executing. To see how the theorem prover can show the validity of this query, let's expand A and B from their definitions. Note that in this case, B was applied to sigma 1 prime and sigma 2 prime. The theorem prover can now show that the resulting states are equal because the initial states are equal and the statements being executed are the same. It can show that I is less than E in the left state because the left path just took a branch requiring I be less than E. And similarly, it can show that I is greater than or equal to E minus 1 in the right state because the right path just took a branch with I greater than or equal to E minus 1. Thus, the theorem prover can determine the validity of this query fully automatically using simple decision procedures and no inductive reasoning. In this case, the theorem prover was successful, but consider some other A and B where A is not strong enough to imply B. In this situation, the theorem prover will not be able to show that the query is valid. PEC would now strengthen the invariant at A so that it does imply B. Specifically, PEC will strengthen A by simply anding in B of sigma 1 prime and sigma 2 prime. Now, because invariants must be in terms of only sigma 1 and sigma 2, we'll re-express the sigma 1 prime and sigma 2 prime in the strengthened version of A using the equalities shown here on the left. The strengthened A will now imply B, but it puts a greater burden on the predecessor invariants of A, which may in turn need to be strengthened. PEC will iterate in this way, strengthening invariants and checking them with a theorem prover until it reaches a fixed point, and we no longer need to strengthen. Note that PEC will never strengthen the invariant at the entries of the programs because we're not willing to assume anything stronger than state equality at the entrances of the 2 programs. Fortunately, the theorem prover can check the A to B case, so we don't have to worry about strengthening here. Similarly, the theorem prover will be able to check all 5 of these cases. Thus, PEC can check that these 2 parameterized programs are equivalent. That is, when they start in equal states, they'll end in equal states. Therefore, our loop peeling rewrite rule is correct. The loop peeling example I just demonstrated shows how we've adapted the relational approach from translation validation to prove optimizations correct once and for all. In general, relational approaches work well for structure-preserving optimizations, which are optimizations where the control flow structure of the original and transformed programs match up well, so that they execute roughly in synchrony. To handle non-structure preserving transformations, we've also adapted the translation validation techniques of Zook et al., which I'll briefly show you next to give you an intuition for how they work as well. Here's an example of an optimization that is not structure preserving, loop interchange. This transformation swaps the order of an inner loop and outer loop so that the original program iterates over R1 and then R2, while the transformed program iterates over R2 and then R1. To prove such optimizations correct, PEC first generates a correspondence between the loop indices of the 2 programs. In this case, the correspondence will state that the ij iteration on the left corresponds to the mn iteration on the right. Next, Peck will ask a theorem prover to show that the side conditions imply that this correspondence is 1-to-1, which shows that the indices in the transform program are a permutation of the indices in the original program. Finally, Peck asks the theorem prover to show that the loop body commutes in the appropriate way, where two statements commuting means that the order in which they execute does not affect the outcome they produce. Alright, so far we've seen how to express and apply optimizations in our system, and how Peck is able to check these optimizations for correctness. Now I'll wrap up by showing you the optimizations we implemented and checked for correctness in a comparison with the rhodium system. To facilitate this comparison with rhodium, I've split the optimizations into three categories. The first category covers optimizations where the Peck and rhodium formulations are equivalent. These include simple optimizations that transform one statement at a time, like copy propagation or common subexpression elimination. The second category includes optimizations where the Peck formulation is more general and easier to express than the corresponding rhodium version. For example, in Peck, loop invariant code hoisting is fairly straightforward, but in rhodium it requires a carefully crafted sequence of insertions and deletions that each transform a single statement. Furthermore, the Peck approach can hoist large pieces of code, including conditionals and even loops, while rhodium is limited to lifting single statements of straight-line code. Finally, the third category includes optimizations that we checked with Peck, but that could not even be expressed in rhodium. These are all complex loop optimizations that require simultaneously rewriting multiple statements. For example, software pipelining and loop unswitching. In conclusion, I've shown parameterized equivalence checking, a technique that proves compiler optimizations correct once and for all, fully automatically, and before the compilers ever run. We achieve this by adapting traditional translation validation techniques to the setting of parameterized programs. In this generalized setting, we check that all runs on an optimization are correct instead of a single instance. Furthermore, we perform this check early, when the compiler is built. Finally, we handle a much larger class of optimizations than previous fully automated systems. This is due to our support for many-to-many rewrites and the subsequent increased expressiveness of our system. Specifically, we're able to fully automatically check the correctness of even complex loop optimizations. Thanks for watching. If you have any questions, please feel free to email me or check out my website. Have a nice day.